So up next, I want to introduce Mr. Salvatore Monte. Salvatore is a renowned expert in polymer science and sustainable materials. He's the president and owner of a leading materials company called Kenrich Petrochemicals. He's dedicated his career to advancing recycling material innovation, which is not easy in this world. A member of the Plastics Hall of Fame and a notable leader in sustainability, Salvatore has contributed significantly to the field with an amazing 34 U.S. patents. I can't even imagine. An extensive research on titanate and zirconate, if I got that right, coupling agents. Beyond his technical contributions, he has lectured worldwide, authored a widely distributed reference manual, and even testified before U.S. Congress on trade and intellectual property protection. Today, he'll be sharing his insights on advanced mechanical compounding, PCR, with TiAl catalyst coupling agents. So please join us in welcoming Salvatore Monte.
Let me just talk, and then you guys can catch me later. All of this information is on my website, www.forkenrich.com, www.forkenrich.com. In that, there's a technical screen with technical links, and you can link on to many of my slide presentations. I've given thousands of them. I have over 500 ACS cast abstracted works. The bottom line is that this is really polymer chemistry, and I find most recycle audiences don't understand half of the things I say because they're not immersed in the chemistry of polymers. But in the area of post-consumer recycle, that is really where the important solutions to recycle exist. Most people try to mix polymers. Post-consumer recycle will consist of polymers 1 to 7. Each polymer is a class like addition polymers, condensation polymers. And even if you take 2 addition polymers, like polypropylene and polyethylene, they are incompatible with each other, even though they're both straight-chain addition polymers, both made with xenon catalysts. The problem is the CH3 off of the on the polypropylene doesn't like the straight-chain polyethylene, and they separate. So you have people collecting post-consumer recycle curbside. They grind it up into nice chips, clean, and they go to make something, and you don't get good material because the polymers are being chain scissored during the melt processing when they're made into a material. And then when they're cut up into small pieces and go through an extruder again, they're even made smaller. Polymers are made by the polymerization of many MERs. And as a result, you get shorter chains. And the shorter chains give you poor properties. So you combine the fact that you have incompatible polymers, the fact that when you melt process them, you shorten the chains. Recycling or post-consumer recycle is very, very difficult to understand and get it to work. The problem is that polymers fall into 2 general classes: addition polymers and condensation polymers. Addition polymers use Ziegler chemistry, which is Julio Natter and Ziegler got the Nobel Prize back in the 50s for inventing these polymers, and they use titanium aluminum chemistry. I have invented a series of large molecule titanates that can take the heat history of a polymer melt. In addition to that, I've combined them with a filler material which has a new chemical unit, and the combination is called KPR for Kenrich Plastic Recycle. These materials we master batch into powder or pellet form, depending upon the end compounder's capabilities. But most people like the pellets because they're working with little scraps of the recycle, and they add these pellets, and they really are catalysts in a concentrated form, which regenerate the polymer in the melt phase. So my titanate aluminum chemistry in the form of a master batch pellet at 1.5% by weight of the recycle, added like a color concentrate, will cause the polymer melt to regenerate itself and in effect cause a new copolymer that actually polymerize all the polymers of the system. I have slides on my website showing a mixture of PET, that would be a Coke or soda bottle or water bottle, with HT. Mix those together. Typically, if you look at a scanning electron micrograph of that, they are totally incompatible. You put the coupler gauge in and they become a tripolymer. So what you have is the ability to catalytically use the extruder as an reactor to create a new composition. In addition to the polymers in a cycle, there are fillers. Fillers come into two general categories: inorganics and organics. Inorganics could be metal oxides by TRT, zinc oxide, or Portland cement is a mixture of different metal oxides. You can have other things like clay and talc and silica. You can have fiberglass. You can have graphite, Kevlar. You can have all kinds of reinforcing materials. And then you have organics like grease, oil, hydrocarbon. And we can react with those materials. Now, I don't know if many of you are familiar with silane chemistry, but the invention of plastic cars and plastic compositions only became possible with the invention of silane coupling agents. And silanes are based on tetravalent silicon, which puts organic chemistry on the silicone, and that proton, they're coupled to a mechanism called hydrolysis and links the silane to the interface of, say, a glass reinforcement, which leaves pendant organic group is then compatibilized with the polymer phase, and then you're able to make plastic cars. Not really plastics, they really indicate peroxide cured or unsaturated polyester. And they call them plastic, but they do your thermoset. They're not thermoplastic, they're thermoset. The difference between a thermoplastic and a thermoset is one is cured, the other isn't. But in any case, silane chemistry existed in the 50s and 60s and 70s, which to you guys is over 70, 75, 80 years now. And it's entrenched in the mindset of investigators looking at trying to compatibilize the similar materials. And as Mark Twain once said, it's not what you don't know that'll get you in trouble. It's what you think you know that ain't so. And what it is that they had this concept that fillers like calcium carbonate, certain metal oxide, carbon, oil, are contaminated in recycle and have to be cleaned and removed, which makes it virtually impossible to use post-consumer recycle. In addition, you talk about the composting issue. You have the same issue with post-consumer recycle. People like Chemical Waste Management, which is the largest post-consumer recycle collection in the United States, will not allow you to put vinyl or any of the condensation polymers into the recycle. Well, most consumers don't know the difference between 1, 2, 3, 4, 5, 6, and 7, and they just throw them all together anyway. So you have the major corporations saying they won't accept vinyl, they won't accept condensation polymers like polyethers, and that really limits the ability to take post-consumer recycle and make usable materials. So most PCR goes as a waste stream or as a feed, a filler feed to work it off, but it really isn't relied on to give you any compositional strength to any degree. So with my chemistry, I proton coordinate with inorganics and organics. For example, the last patent I got was on January 25th, 2025, which was nanosurface modification of Portland cement. And if you look at Portland cement and you look at the interface of Portland cement, it really consists of 5 different metal oxides. I can proton coordinate a titanate onto that surface and make the Portland cement both hydrophilic and organophilic. And as a result, you're able to decrease the cement to water ratio by 31%. And you also allow it to be compatible with oil. So you could take oil soaked sand from an oil spill, mix it with Portland cement and my material, and make a useful concrete composition. So the underlying message of my talk is that with organometallic chemistry of titanium and aluminum, you can couple to inorganics and organics, and you can catalyze polymers 1 to 7. If you put that chemistry into an extruder, it will take and compatibilize all of the similar materials, and out the other end will come a material which has to be defined as a useful material that will give you strength and the properties of the materials that go into it. One of the biggest problems I see with post-consumer recycle is that eventually they're going to have to create standards as to if you take a mixture from different neighborhoods and they may be Greek, Italian, or different countries, you have different mixes of people who use olive oil. Some people don't use olive oil. You have to classify the recycled material. What is its mechanical property? If you're selling polypropylene or polyethylene virgin material, you list the melt index, you list the molecular weight, you list the properties like tensile, elongation, etc. This has to be done with post-consumer recycle, which hasn't even begun yet. So post-consumer recycle is really in its infant stages and being used really just as a waste stream filler. It will become useful as a material in and of itself when they start using the catalysis chemistry of titanium and aluminum, which is used to make the polymers to begin with, and the chemistry of interfacial surface modification, which is also available to silanes, titanates, and zirconates. That's the essential underlying message that I had to give you guys this morning. There's all kinds of applications from I have patents on preventing the unplanned detonation of explosives because I take the nitramine, which is an organic material. I put an atomic monolayer of phosphorus titanium on the surface of the nitramine, cellulose acetate plastic binder, and are able to make a better explosive, more powerful, but safer. I am the long-lasting lipstick that you women use for L'Oreal, Mac Factor, Maybelline, CoverGirl. I'm on long-lasting eyeshadow. I'm in 700 improved formulations for cosmetics in Europe. It goes on and on. I'm on the videotape that you used to have the hiss went away with a pyrophosphatidyltitanate on the gamma ferric oxide. When you take a photocopy now, you get a clear reproduction. You can't tell the original from the copy. My material is deagglomerating the material, the gamma ferric oxides to make them clear. The same with the pigments. So it's a way of taking pigments and inorganics and organics and compatibilizing them with polymer phases. And we make them in liquids, powders, and pellets. We are ISO 9001 certified for production and for managing the process. I've been, my first invention was 1973. I've been doing this for over 50 years. I've given thousands of presentations. It's too bad you couldn't see the 179 slides. We've overwhelmed you with a lot of photos and pictures and illustrations. But if you see a Wilson titanium golf ball with the word titanium on it, and you learn that it's my material in there that's increasing the coefficient of restitution, it simply means that I'm allowing the rubber to become more elastic and more flexible, which is critical to mechanical properties in recycled materials. Generally, that's my presentation. I'm sorry I don't show you pictures, but illustrations are pictures worth 1,000 words.
Well, thank you, Salvatore. Without the pictures, that was an amazing job of summarizing something extremely complex, well beyond my knowledge base, but I feel like I've already gained some information here just from your verbal presentation. So thank you so much. Are there any other questions in the audience? Feel free to unmute yourself.
Okay, thank you.
Does anybody have any questions? I have a quick question. So you're talking about ordinary Portland cement, and I didn't quite catch how you were making the hydrophobic and the hydrophilic stuff get together. Elaborate 1 minute about that.
Yeah, it's very, very cool. Yeah, in order, most of the organometallics that we make are water insoluble, which is important in processing in plastic because you don't want to have the material exposed to the atmosphere and hydrolytic would decompose. So we make them hydrolytically stable and water insoluble. Okay, so now when you go to make an interface of a Portland cement, which is mixed with water in order to make the thermoset called plastic, called Portland cement, you need to have a reaction of the Portland metal oxide cement with the water. Well, if you put a titanate on there that's water insoluble, you're making it hydrophobic, and that defeats the whole purpose. So what you have to do is uh, formulate a titanate ester that has a water emulsifiability so that the emulsion of the titanate in the water phase gets to a point where it's operating at the atomic level. Took me about 10 years to do this. Okay, so it doesn't happen overnight. And everything that we do in the significant takes decades. I mean, even Gillette, who invented the safety razor blade, it took them 5 years to find somebody who can hack the blade that got the patent on. All right, it just takes time to develop the thing. But the answer to your question is, we formulated so that you put atomic monomer of hydrophobicity and hydrophilicity on the material, and that gives you both functions. It works in membranes for hydrogen gas powered cars with carbon, etc. So it really is sophisticated chemistry, and I don't understand half of it because it has to be really characterized, and you need electron microscopic laboratories. You need atomic force spectroscopy. You really need a lot of. So it's almost the Holy Spirit guides you in this stuff. Invention's a weird phenomenon. We're truly innovative inventing. I do things. I stood before the American Defense Preparedness Association in 1983 and told them I could solve the problem of unplanned detonation of the propeller of the day tank with absolutely no information on the fact that I could foam cool floats and make them bigger. I could take screwdrivers and make the handles more defined, and I could stop flame retards, flame spread of a polypropylene by coating the calcium carbonate with phosphate or titanate. I said, look, nitramines, explosives are really just foaming agents that they make cool floats out of. Screwdriver handles of cellulose acetate butyrate. That's the plastic binder, blah, blah, blah. I gave them all these commercial analogs. I said, it should work on the ammunition. Well, 8 years later, I got my first order.
Oh, wow. So much. Hey, could you just put a link in the chat to your article so I can take a look more closely?
.4cameras.com. Okay.
Thanks so much.